Okay, good morning, everyone. Today we'll look at the equations for voltage, current, power, and energy for an inductor, and then get into the physical construction of a capacitor for a little bit. Okay. So let's share. All right. Okay, we stopped here last class. Inductor physical construction is nothing but a conducting coil wound into spiral loops. Okay, multiple loops. Each loop is known as a turn. Is known as a turn of the wire, okay, turn of the coil. So the equation is given by L mu n square A over L. The uppercase L stands for the inductor value. The lowercase l is the length of the coil from end to end. From end to end. Okay. N is the number of turns, as I said. So N, so each loop is one turn. And so the number of turns, now here it lists as 100. It's not 100 turns in here, of course. In this figure, I can see exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 turns. Okay, so it's not 100, but I can see 12 turns. All right. And A is the cross-sectional area of each loop. Okay. And the assumption, of course, is that the inductor is wound around a magnetic material, right? Typically, there is some sort of magnetic material inside within each loop. So the A is the cross-sectional area of that spiral coil. You can, of course, construction, we would know the radius or you would know the diameter and calculate the area from there. Mu is the permeability, and further is given by mu 0 times mu r. Mu 0 is the permeability of free space. It's a constant. The value of that constant is 4 pi into 10 raised to minus 7 Weber per meter square. Oh, Weber per ampere meter. Always forget the ampere. Now you can have all of this in your equation sheet, okay? So you don't have to memorize any of this. And mu r is the relative permeability of the core material. Okay. The center of that loop is known as the core, or is called as the core of that inductor. If there is nothing present inside that center, then it's an air core inductor. But typically, again, if you recall a couple of slides ago, I showed a slide which has a magnetic material inserted through the core of the inductor to increase the magnetic field strength. And so typically we would have a core made up of iron, steel, nickel, cobalt. All of these materials have, yes. Hold on. Oh, 0 and R. 0 and R. So R is the relative permeability of the material of the core. 0 is with respect to free space or vacuum. Yes. There are actually many units for those, but it's named after a person, Carl Weber, or can't remember the first name, but it's Weber. So WB stands for Weber. And magnetic flux density, Tesla. Again, it has, depending on the application, depending on the person, depending on the industry or the field, they all use different units. Okay. But sometimes, as I said, sometimes it's named after a person associated with that quantity or with that component. And so in this case, it's named after Weber, and the magnetic flux density is named after Tesla, 1T. What else was there? And then, of course, the inductor value is named after Henry, Joseph Henry, and so it's labeled as uppercase H, Henrys. Now, typical inductor values are in the millihenry or microhenry range. Okay, most of the inductors and capacitors we use, it's kind of the opposite of a resistor. Resistors are usually in the hundreds or the thousands, so usually like kilo ohms or larger. And capacitors and inductors are in the millihenry or the microhenry range. Let's see what else was there. Oh yeah, mu n square A over L and mu 0 times mu R. Oh, relative permeability does not have any units. Okay, it is the comparison of the permeability of the material with reference to mu 0. So it's a dimensionless quantity, no units. Some examples of real-life inductors. You can see the small ones. These are typically the size of resistors. Resistors that we see in real life. So I would just say resistor size. But if you want an inductor which has some higher value or some high current carrying capabilities, then you would actually use a core inside it. And most of the cores come in the shape of a toroid or toroidal inductors. Okay, toroidal high current inductors. So if you look carefully, the size of the first and the second one, big difference in the thickness. Okay, the thickness has nothing to do with the level of the inductor. Okay, the inductance level. So the thickness of the coil has to do with the current carrying capability of that wire itself. Thin wire, just in general, if you have a thin wire, it can carry less amount of current. Thicker wire can carry large amount of current. Okay, which is also the operating principle behind an electric fuse. You have a fuse physically constructed with a thin wire. If the current passing through that wire increases beyond the capability of its construction, then we say the fuse blows. Well, what exactly happens is the current flowing through there causes so much heat to go through that it just breaks the connection. And so thicker wire, large current carrying capacity, thinner wire, low current carrying capacity. And you can look here in the values, 10 amps versus 1.3. 10 amps, by the way, is a huge amount of current. Okay, it's a huge amount of current. Even if we operate like heavy machinery, the current carrying capacity in there would be 15, 20 amps. So 10 amps is a huge amount of current. It's very large. Typically, electric and electronic circuits deal with currents on the order of milliamps, sometimes even microamps. Okay, milliamps or microamps. The USB spec is 5 volts and 0.5 amps, which is 500 milliamps. So 10 amps, again, is a huge amount of current. If you look at the number of turns, very, very low. So N is low, N is high for the first two inductors that are shown in here. And so you can see that reflected in the value of those inductors. Again, inductor value is directly proportional to N, directly proportional to mu, indirectly proportional to the length. In this case, the number of turns is high, so the inductor value is high. And the third one basically reflects high number of turns plus a longer length. Right? The length increases. The length would be measured like this. Okay. And the inductor value is inversely proportional to the length. So the longer the length of the coil, the lower the value of the inductance. So even though it seems big, the inductance value is not that much different from the previous one. It's actually exactly the same, except the current carrying capability is a little higher. Okay, so just real life examples based on the physical construction of the capacitor. The major equation that governs voltage and current relationship is V equals L di over dt. Voltage is directly proportional to the rate of change of current flowing through that inductor. Remember, I said if current is constant through the inductor, then the voltage across that inductor is equal to 0. If the current changes, then energy is being transferred and released back into the circuit. Okay, then it causes a voltage to appear across that inductor. Oh. So again, V is directly proportional to the rate of change of current, di over dt. The proportionality is given by the constant L, which is basically the inductance, the value of the inductor itself. Okay, hence V is equal to L di over dt. The flip side of that equation gives us the current equation, right? V equals L di over dt. If you want to find current given the voltage, then you simply integrate both sides of the equation. L is a constant. You take it outside and take it to the other side. It becomes 1 over L. Integral V, and this is I. Okay, and that's reflected in this equation right there. And I will explain each term in there. Right, so V is directly proportional to di over dt, and then I is the integral of V. So just to give you a brief explanation of that expression. When an inductor, and for an inductor, we always talk in terms of input current. Okay, so current is being applied, which causes a voltage to appear across the inductor. For a capacitor, it's the opposite. For a capacitor, we talk in terms of voltage. So applied input is always a voltage. So on the x-axis, we have time. On the y-axis, we have, let's say, we have either voltage or current, doesn't matter. Okay, voltage or current. If we apply, let's say, a constant level of voltage or current, fixed or constant value of the current, the energy that is now being transferred to the inductor cannot change in an instant. It cannot go from 0 to 1 amp in an instant, right? It takes some time for the energy to be transferred. So it follows this path. It's exponential in nature. Okay, and we'll study that in chapter 4. Study that in chapter 4. Once the inductor receives all possible energy, it reaches a state where that doesn't change anymore. And that level is known as steady state, which is there in the next slide. Okay. So if you apply a current after some point in time, is going to reach a steady state. Now, if you want to find the voltage from this applied current, we simply use this equation, V equals L di over dt. But now if you want to find current, if you are given the voltage, you simply integrate, and the integral, well, 1 over L is self-explanatory. We simply took it on the other side, so reciprocal of the inductance value. But what we're doing is we're integrating the voltage between a certain time period. Integrating in simple terms is simply adding up all the individual slices, right? dt is just individual slice, and you add up all the slices. But take a look at t0 and t. What are we saying here? We are saying that the voltage and current are a function of time, meaning the value of that voltage or current changes depending on the time instant where we are looking at it, right? So if you look at, let's say, if you look at a point somewhere in here, that t would have some value. Microseconds, milliseconds, 5 milliseconds, or 10 microseconds, or whatever, depending on your analysis of the system. So t is the variable. Okay, t is the variable because the voltage and current is a function of time. So when it states I of t, it's simply stating the current as a function of time. That time is the variable. It could take multiple values. Could take multiple values. So t is the variable. And t0 is the beginning of time. Not literally the beginning of time, but it's simply the point at which you begin your analysis. Okay, the point at which you begin your analysis. And even in that, it's the point in time where you begin your analysis. Okay. But for example, let's say you're working with a system that goes from 0 to 10 seconds. Okay, 0 to 10 seconds. You can break up this 10 seconds into multiple parts. You can break it up into 10 parts. You can break it up into 100 pieces or 100 parts. You could break it up into 1,000 parts. Doesn't really matter what it is, what the purpose is, but there is a definite time period for your system, 10 seconds, and then multiple parts in there. Let's keep things simple and say you're analyzing between 5 to 7 seconds. So in this case, you're analyzing that system from time t equals to 5 to time t equals to 7. So for that analysis, the beginning of your analysis is at 5, and hence t0, the value of t0 would be 5. Does that make sense to everyone? So again, t0 is the point in time at which you begin your analysis. Sometimes some authors like to use the notation I, okay, instead of 0, and we will see that in chapter 4 also. So let me write it. 0 or I, and that I stands for initial value. Okay, I stands for initial. So it could be either t0 or ti, the initial value. I don't like to use I because I is already there for current, so sometimes it can get confusing. right? So it's simply the integral of the voltage. You're simply adding up the voltage between those between those times from 5 to 7 seconds. Make sense? Right? And then we have the stored energy. The stored energy. So remember, I said T0 is simply the point in time at which we begin our analysis. In this example, it's 5 seconds. So we add on, or we have to count any stored energy in that inductor from a previous point in time. So if you begin your analysis at 5 seconds, then you also have to account for the energy that was stored in the inductor at the beginning of your analysis. And that is what this this quantity represents. I of T0 is the stored energy. So the previously stored energy in that inductor or capacitor. Okay. And that's it. We are not going to go much further than this. There's a couple more equations about power and energy, but we won't go too much. We'll just snorkel the surface. Remember, I said that. Non-E major class, we're going to skim the surface. We won't go scuba diving. We'll just do snorkeling. So, any questions about this equation? Make sense? Right? Now, the stored energy value would be a constant. It may or may not be explicitly stated in the problem statement, but it would be your job as an engineer to actually look at the problem and the problem statement and then extract all the information from there. All right? Okay, any questions? Yes. Yeah, if it's a function of time, you just say V of t. Sometimes they are used interchangeably. Sometimes they are mentioned. Sometimes they are not. So sometimes this equation would just be like, I is equal to 1L and so on and so forth. It would not even state it's I is the function of time. So it's simply given to be understood that it's a function of time. Yeah. Only to that point. So sometimes this V is written as V of t. Some books I've seen it, some books I haven't. Okay. I used the subjective line where I said, if you apply a constant current to a inductor, the voltage across it is 0, right? And that is borne out by the equation. Voltage is L di over dt. If I is a constant, right hand side is 0, voltage is equal to 0. Doesn't matter what the inductor value is, right? Mathematically, we can see it quite easily. If I is a constant, meaning a DC current is applied to an inductor, once it reaches steady state, meaning it reaches that level of current that is being applied, from that point on, the voltage is equal to 0. So if we had a meter and we connected it across the inductor, depending on how fast or slow the circuit is, or how big the inductor is, we would see a voltage until the point where the inductor reaches full charge. And once it reaches full charge, that voltage would go to 0. Make sense? So for a DC source or a battery, DC source or battery is of course DC. Inductor voltage VL would always go to 0 volts. How fast or slow it goes to 0 depends on the values of the components and the current that is being applied. But eventually it will go to 0. When it comes to AC, it's different because AC always keeps fluctuating. So it goes through positive, negative, positive, negative. So there's constant change all the time. But for DC, the behavior of an inductor is said to be 0. It behaves like a short circuit. Okay, so di over dt is 0, and hence voltage VL would go to 0 volts. So DC behavior or steady state behavior is that inductor behaves like a short circuit. The not flip side, but the conversely, a capacitor behaves like an open circuit. And we'll see that when we get to a capacitor. Okay. All right, power equations. Electrical power is still the same expression. P is the product of voltage and current. P equals VI. Simply plug in the values for V, the equation for V, and you obtain Li di over dt. Okay, Li di over dt. And then, of course, power is the time rate of expending energy. So W is half Li squared. This is the total energy stored in the inductor. So if you already know the amount of current that we are applying, especially if it's DC, then we can simply calculate the total energy that is being transferred. It's half Li squared. Capacitors have a similar equation, half CV squared. At the end of this chapter, I have a slide which lists or summarizes all of the equations for both inductors and capacitors. Again, you can have those on your equation sheet. You do not have to memorize them, but you do have to understand them and know when and how to use them. Okay. All right. So before I move on, any questions? Any questions about inductors? Yes. Good questions. The question being asked is, do the inductors have resistance? And the answer is yes. Real life inductors actually have resistance. And if you're taking the lab, you will see that the inductors that we use for in 251, depending on the quality, we have both high quality ones as well as low quality ones. So quality factor is a real term that describes Q. And again, typically this is not something we do for non-E class, but since the question has been brought up, Q is the quality factor that describes the resistance of an inductor. Now, typically the resistance is measured, it's part of the coil itself. If you take a piece of wire or conducting material, and if you measure the resistance between the endpoints, again, this is not part of the course, but again, just this concept, R is given by rho L over A. Rho is the Greek letter rho, R-H-O, material property. It's the resistivity of the material. Okay, this is the resistivity of the material. And L is, of course, the length, and A is the cross-sectional area. So if you take this piece of wire and you make an inductor out of this wire, that wire will still have resistance. Make sense? Right? So depending on the quality of this wire and the construction of that inductor in real life will also have some resistance. High quality inductors have resistance on the order of like 5 ohms or less. Okay, 5 ohms or less. So quality factor is typically a ratio of, I'm going to think it's L over R, or I know it's inversely proportional to the resistance. Ideal inductors, of course, have 0 ohm resistance. So the quality of an ideal inductor is infinite. But real life, that resistor will have like, values. I mean, the inductor will have resistance values 5 ohms or less. If you're taking 251 and you're doing lab 5, where you would use inductors, those inductors have some resistance. And let's see, it's about 100 ohms for that inductance level that we use in the lab. Okay, So that's significantly high. 100 ohms is really high. Anyway, that's the concept of the resistance. Yes. Yes, it does include that. Yes. It's also sometimes it's also referred in newtons also. Oh, you're talking about this equation. Yes, yes. Yeah, that's standard. That's the standard energy. Yeah, that's standard. And that should be lowercase. All right. Any questions before we move on to a capacitor? All right. So capacitor, we'll start with the physical construction. It's nothing but two parallel plates, two conducting parallel plates separated by an insulating material. So conductor and an insulator. Okay, dielectric is the insulator here. You could take your two hands and put them together, separated by air. And if you had a meter capable enough to measure this low capacitance, you would see some value. So you put your palms together like this, close together, and you can measure capacitance between the two palms of your hand. But again, it would be very, 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 very small. Okay, very small capacitance that could not be measured. Symbol for a capacitor to represent two parallel plates is just two parallel lines of equal length. One end could be concave, curved. If there's an arrow going through a component, which isn't something I actually pointed out earlier, whether it's a inductor, capacitor, or resistor, that arrow simply notes that the value is variable or the value can be changed. Okay, the value of the resistor can be changed. A variable resistor, and this is always funny, a variable resistor is also known as pot, short for potentiometer. And so we always like to joke, E is use a lot of pot, because we use variable resistors in many circuits. Anyway, so that's the basic construction of a capacitor. We'll look at the equation in just a couple of slides. So capacitor charging. For capacitor, we always deal in terms of voltage. So voltage is being applied to a capacitor as input, and then we deal with the voltage and current equations from that point on. Capacitor, as I said, the name comes from the capacity to store energy, right? So the energy is stored in the form of charge, electric charge. So in these four figures right there, A, B, C, D, the first one shows that a capacitor is being connected to a battery separated by a switch. Initially, the charge present on the capacitor is 0 volts. Okay, charge is 0 volts. Once the switch is flipped, the voltage source Vs is connected to the capacitor. And once it gets connected to the capacitor, what happens is the electrons on the plate connected to the positive end of the source are attracted by the positive charges. So the electrons move away from the capacitor plate, thus leaving behind an excess positive charge. Okay, if an electron moves away, it leaves behind an excess positive charge. On the other side, the negative end of that voltage source repels the electrons in the wire, and the electrons build up on the other side of the capacitor plate. And so thus, you have a buildup of positive charges on one side of the plate and negative charges on the other side. You measure the difference in potential between those two plates, which is nothing but voltage. And that is the capacitor voltage, VC. And that is simply the operating principle of a capacitor. In electrical engineering, and you may have learned this in physics, current always flows the opposite of an electron. Right? If electrons are moving one way, we say that the current is moving the opposite way. So it's also known as electron flow and hole flow. In semiconductor device physics, when an electron leaves its place, then it leaves behind an empty spot. That empty spot is known as a hole. Literally, it's a hole. They couldn't come up with any other term. And so we have current flow, that is the opposite of electron flow. And then we have hole flow. So current is taken in the direction of the flow of holes. Okay, hole flow. But again, we won't get too much into the physics of things. Yes. Sure. So when you connect the positive end of a battery to this plate, the positive charge, sorry, not positive charge, the electron starts, well, not start, it gets attracted to the positive end of the voltage source. And so thus, when the electron moves away from that plate, it leaves behind, or not leaves behind. If you had 100 electrons and 100 positive charges balanced out, if one electron moves away, you now have one excess positive charge on that plate. And so that charge starts accumulating for every electron that moves away from that plate. On the other side, the negative end of that battery repels the electrons, and they start accumulating on the other side of the plate. The key to the operation is that the two plates are separated by an insulating material, so they cannot cross over. So once the charge starts moving, it cannot cross over. We have electrons, and I'm doing the representation in my direction, but the electrons are moving in this direction, right? So the top of the plate, it's moving in this direction. At the bottom of the plate, it's moving in this direction. Am I doing it right? Yeah. So it's building up the electrons at the bottom plate, and positive charges are built up on the top plate, but they cannot cross over because it's separated by a dielectric. So physically speaking, and again, without going too much into the physics of things, physically speaking, the electrons are moving, but they get stopped across the plates of that capacitor. They cannot cross over. Does everyone understand this? Right? They cannot cross over. Charge is built up. So even though electrons are not completely crossing through the capacitor, we do say that the current is flowing through the capacitor. Okay, important to understand that. Let's take a 10-second pause. We think over that and let me know if you have any questions. Okay, it cannot cross over through the plate. Okay, the electrons are stopped. They stop right here. They cannot cross over. So even though they are not crossing over, we still use the term that current is flowing through the capacitor. Physically, not possible. But schematically, we do say current flows through the capacitor. Going back to chapter 1 and physics, what is 133 and 143, right? Current is the rate of flow of charge. When charge flows through a conductor, we describe that as current. So since the charge is flowing through that circuit, we say that current is also flowing through that circuit, even though physically the electrons cannot move through. One other reason also is that there's a charge imbalance. Okay, the voltage here causes an imbalance across. If it's 0 volts across the capacitor, and there is some voltage being applied on Vs, there is an imbalance between Vs and Vc. Okay, but once Vc reaches the value of Vs, there is no more imbalance. And we say the capacitor is fully charged. Okay, fully charged. The capacitor has stored as much energy as it can. It reaches full charge or maximum charge, and that's it. Now, obviously, in real life, we would never connect a capacitor that cannot accept Vs, right? If a capacitor is rated for 8 volts and you apply 10 volts to it, you might damage the capacitor, depending on the physical construction of the material and how strong it is. So if you're applying like 10 volts, you would always ensure that the capacitor can accept more than 10 volts. All right, what we are showing in D is once the capacitor reaches full charge, you can actually remove the capacitor from the circuit. You can remove it from the circuit and it will hold that charge. Ideal capacitors can hold the charge indefinitely. Nothing will happen to it. But in real life, it will get discharged. Slowly but surely, that VC will go to 0. And again, it depends on the size of the bucket and how much water is in the bucket. So basically, it depends on the size of the capacitor and how much voltage we apply to that capacitor. But it will go to 0 eventually. Because in real life, no insulator is 100% perfect. Right? It's separated by an insulator. So if 2 plates are separated by this insulator, a real life insulator cannot separate out 2 plates or 2 charges for infinity. The charges will actually discharge through that insulator itself. Okay, if you take a charged capacitor and leave it out, depending on the size of the capacitor, it's going to discharge either in a few seconds, a few minutes, or if it's like a really huge capacitor, maybe a few days, but it will go to 0 eventually. Because the same separation also means that the 2 plates are joined together. We use the words that the plates are separated by an insulator, but it also means that the plates are joined together by that insulator. And so that allows a pathway for the charge to get dissipated through that insulator. And going back to that point about resistance of an inductor, resistance of an inductor is always noted as series. But resistance of a capacitor is noted as in being in parallel to that capacitor. So electrically and schematically speaking, if you had a charge on that capacitor acts like a battery and discharges through that internal resistance of that capacitor. Okay. Internal resistance. And similar to quality of an inductor, we also have quality and dissipation factor for a capacitor. Yes. Yes, that is correct. Real life inductors and real life capacitors are modeled as an ideal inductor along with a resistor. So a real life inductor, and this would be a real life capacitor. Again, 201 lecture classes, even for EE lecture classes, everything that we do, every analysis we perform is always with ideal components. Okay, we do not take into account the non-ideal factors. Make sense? So if you take a capacitor, charged capacitor, remove it from the circuit, and you short the two leads together, what do you expect happens? What do you think might happen? Small spark. Yeah, it discharges, but it discharges in an instant. So large amount of energy, again, depending on the size of the capacitor, is released in an instant, causes a small spark. If you take a huge capacitor, charge it to, like, let's say hundreds of volts, and then you short the two terminals together, you are now releasing hundreds of volts all in an instant, then you might have an explosion. But again, that's not something that people do. So we always use a resistor like this. And so the resistor will slow down the current. It also provides for a discharge path for the capacitor current to flow through. The energy is slowly transferred to the resistor, and the energy is dissipated in the form of heat. There are videos floating around on the internet where you can actually see people might charge a capacitor and then short the terminals. And capacitors, like inductors and resistors, are passive devices. They do not have any energy of their own. They can only receive energy, store it, and then release it back into the circuit. And that stored energy is, is associated with an electric field. So it's a passive component. It follows the passive sign convention or the passive reference configuration, meaning current will always flow from high to low, from plus to minus. Okay. If you're given the voltage polarity for a capacitor, then the current direction should always go from plus to minus. If you're given the current direction for a capacitor, then the polarity, the point of entry is always plus and point of exit is minus. Same thing as a resistor, same thing for an inductor. Simple examples of what a capacitor would actually mean. Remember, capacitor is the capacity to store electric charge. Okay. Mathematically speaking, it is storing electric charge for every unit of voltage applied. So C is Q, the charge stored per unit of voltage applied. So Q over V. Or we can write Q is CV. This is where the capacitor equation comes from. Q is charge, rate of flow of charge, dq over dt is current I, and that gives you C dV over dt. Oh. But anyway, look at these three examples. Depending on the voltage, the capacitor value is inversely proportional to the voltage. So if the voltage increases, then the capacity of the capacitor decreases. Okay. So for high voltage applications, for a similar size, the capacitance value will be lower. And we can see that reflected right here between A and C. If you take a look at A, it can store 6 coulombs for applied voltage of 2 volts, meaning for every volt applied, it can store 3 coulombs. And so the capacitance value is 3 farads. Second one, it can store more charge, 12 coulombs for 2 volts applied, so 6 farads. But now, if you want to use that capacitor, same capacitor for high voltage applications, then the capacitance value is reduced. 1.5 farads. So voltage increases, meaning if you're using it for high voltage applications, then the capacitance, the charge holding capability of those two plates goes down. So from 6 farads goes down to 1.5. All right. And let's see. Actually, I fell behind one slide. Physical construction of a capacitor. The equation is very similar to the, well, not similar. It's given by C epsilon A over D. And epsilon is out of time. We'll pick up here again on Friday because it's already 11 o'clock, so I'll stop right here. All right. I'm available for the next 10 minutes before the next class begins. So if you have any questions, feel free to ask.